Hello there. Today we're looking at CornerNet detecting objects as paired key points by Hai Law and Jia Deng. So on a high level, this paper detects objects in images. Let's say this is an image and here's a chair. You have your chair. And the way you detect the chair for this paper is going to be you detect the bottom right and the top left corners of the bounding box of the image. So rather than detecting the middle and then specifying height and width, like we saw in the Facebook DETR paper, you detect the two corners. And this paper goes through what they have to do to get this to work, including a new pooling method called corner pooling. So that's the gist of the paper. As always, if you like content like this, consider subscribing and sharing it out to other people. That would be very helpful. So a commenter actually recommended this paper to me after I made a video on Facebook's DETR object detection pipeline. I said something like, okay, since that paper always would detect the middle of the object and the height and width, couldn't you make something that detects the corners here and the corner here, and then that would define a bounding box just as well? And in the comments, and thank you very much for that, someone pointed me to this paper. It's a bit older, as you can see, but I still think it's pretty cool. So we've already seen the problem. Like, the problem isn't hard, and it's detecting bounding boxes in images. And in these data set, the problems, the difficult parts are that you sometimes have multiple objects. Like here you have two humans. They can be overlapping. They can be of different sizes. There could be like a third human, like small back here. There can be other objects. You don't know how many there are and so on. So it is a fairly complicated problem. But as I already said, the way that CornerNet here does this is by predicting the locations of the top left and bottom right corner, thereby defining a bounding box. And it does this independently. So there's one network basically that does the top left and one that does the bottom right, and they are then combined, and at the end they're sort of refined, I think. So the architecture is pretty simple. First, you put the image through a ConvNet, which is like a feature extractor. So this is the basic part. It was even the basic part of Facebook's DETR pipeline. First, you have some sort of ConvNet. Now, they, in this case, use this hourglass architecture that I described down here somewhere. And this basically compresses the image into a smaller resolution. So I would take that image and compress it down to very small resolution, but many channels. So it's sort of forced to learn a global semantic representation, and then it upsamples the image again. It downsamples it again, and it upsamples it again through. So at each of these steps, there are many convolutional layers right here. And because that would lose you too much spatial, like local information, there are skip connections built in between pairs of layers where information can travel without computation, basically. So this is fairly standard architecture right here. But then after this hourglass CNN, you get to these prediction modules. Now let me switch back to the top drawing. Because ultimately what you want as an output of these prediction modules is two things. So first of all, you want these heat maps. Sorry about that. And these heat maps will simply tell you where are the corners, okay? Now the heat maps, their dimensions are the height of the image. Sorry, the height here, H, come on. And the width of the image. And this here would be the number of classes C, okay? So you have one channel for each of the classes that you predict. And the heat map will basically be very high at the location and channel where there is a corner of that. So you see you have one heat map for the top left corners and one heat map for the bottom right corners. And then also what you want to predict are these embeddings. Now, simply because you have, I said there can be multiple instances of the same class in the same image. So now you have, in this particular case, you're gonna, even if you predict absolutely correctly, you predict 2 top left corners and 2 bottom right corners. Now, this isn't particularly hard because there's only one configuration that can possibly be, but there could be situations where there are multiple, and that's why you need to somehow match these corners. You have to know which ones of those are the same objects. And they do this by a second output in their heads called these embeddings. Now, these embeddings, they're simply vectors, and the only thing that they're asked to do is they're asked to have a large inner product whenever they belong to the same object, and they are asked to have a small inner product, when they belong to the different objects. So this orange thing here would have a large inner product with this green bottom right corner embedding. Okay, so you train these embeddings. They don't need to mean anything. You simply train them to predict the same thing for the same objects and different things for different objects. So after that, when you match the corners, you can simply go over, you can say, which one of these 2 right here has the larger inner product, or you can do like some Hungarian matching and maximize the total inner product or something like this. This was quite surprising to me that it works, but it's based on a line of research that has already established that this can work, because ultimately these 2 pipelines do not really communicate, right? So I'm going to guess what they learn is sort of a descriptor of the actual object that's there. Because if both describe the objects that's there with their embeddings are going to have a large inner product. And if they describe different objects, then their embeddings are not going to match, right? So even though you train this objective, I still think that these embeddings would pick up something about the object, something about the visual characteristics of the objects. It would be very interesting to see whether someone could actually parse out what they do, because it's almost impossible otherwise for these things to be learnable. All right, so that's the goal right here. You want to get these heat maps and these embeddings, and the way you do it is fairly easy architecturally. You have these 2 prediction modules, one for top left and one for bottom right, and each of them have 3 outputs: the heat maps, the embeddings, and here the offsets are simply a way for you to deal with the fact that you downsample, and by downsampling you have to round certain pixels to certain locations, and then the offsets, they compensate for this. But I don't want to focus on these right now. So you simply have these 2 outputs right here. Now we'll look at corner pooling in a second, but how do you train this? So you can now say, okay, if I have a picture like this, there is exactly 2 locations in the class human where the top left corner is correct, and that's right here, and that's right here. Okay, so 2 locations. So I make my matrix, my target matrix, with a 1 here and the 1 here, and zeros everywhere else. All right, 0, 0, 0, 0, 0, 0, 0, 0. And I train my network to give me this particular thing as an output for this heat map in the channel human. This might work, but it is more profitable, let's say, if you allow for some slack. So what they say is, since if I'm anywhere within this orange circle right here with my prediction, my resulting bounding box is still going to overlap fairly well with the ground truth bounding box. And the accuracy measures for these things, I think, are based on how much you overlap with the ground truth bounding boxes. So what they do basically is they put a 1 in the spot where the actual corner is, and then they put like a 0.9 around it, 0.9, 0.9, and so on, and they kind of flatten out. So this is sort of a Gaussian right here in multiple dimensions, if that drawing makes any sense. And they say, well, the closer you are, basically, the more reward you get. So you train it to predict in this general location. Now, of course, the exact size of this Gaussian has to be dependent on the actual size of the box itself, and they have they regard that and say exactly how they calculate these Gaussians. But for the understanding, it's just important that they do give some slack here in how they compute the loss with respect to the heat map. Now, the loss with respect to the embeddings is pretty straightforward. So remember, these embeddings, you have two embeddings per. You have the top left embedding, that's the ETK, the top corner embedding, and you have the bottom right embedding. And what you want is for them to be close together when they describe the same object, right? So this is this push and pull losses. So in the pull loss, what you want to do is you want to minimize the distances of these two things to this thing right here. And this thing is simply, so EK is simply the mean. So it's ETK plus EBK divided by 2. That's simply, if your top left corner is here and your bottom right corner is here, and they have embeddings, this one has this embedding and this one has that embedding, then the mean of the two embeddings, which I guess is whatever, this right here, yeah, that's about the mean. So the location is not important, actually. So it's about the embedding vectors. It's not about where the corners are. The two embedding vectors must be close together, and you model that not directly by making them close to each other, but by making both close to their mean. And that probably saves you some back propagation troubles, where if you have two moving parts in a loss function and you optimize both, then you tend to, so you have two things, you want to bring them closer together, they might tend to overshoot or something like this. Okay, so this brings those two closer together, and in the push loss, what you want to do is you want to simply make the mean between the two. Remember, this is the mean. The mean embedding of this object far away from the mean embedding of any other object in the picture. Okay, so this here is a margin loss, which means that you cap it at some point. So the if they're close together, if the embeddings of two different objects are close together, you can see here this quantity will be small, and therefore it will lead to this delta. You give a loss of 1. The delta here is 1 in this case. But as they get further apart, you're more and more happy, and you reduce your loss until you don't give any bonus for them being super far apart. You simply don't want them to be closer together than 1. All right. In their case, I think they have the dimension of these vectors is actually 1, which basically means they just output a single number, which I find astonishing that works. Yes, they use embeddings of 1 dimension, so they just use numbers. Astonishing that it works, but okay. So that's how you train the embedding output. Embeddings close together of the same objects of the two corners, and embeddings far apart for different objects. All right, so we can now predict where the corners are, and we can match them. Now, one center part of this is the corner pooling. And why is the corner pooling necessary? So what's the problem with this sort of approach? The problem, and they have an example right here, the problem when you want to predict a corner of an object is that in a CNN, what the CNN is good at is like local neighborhood information, right? So if you have to predict, let's go for the moon actually here. Let's predict the location of the moon. If I have to predict the location of the moon and I'm a CNN and I have this receptive field, I'm like, oh yes, it's like in here. And then I have this receptive field and I'm like, yes, it's in here. And then I zoom in on the corner, not on the moon itself, but on the corner where I need to predict, right? At some point, I'm like, wait, where is it? Because in this particular receptive field at this resolution, I have no clue if the moon is close, right? So at the location where the actual bounding box is, I have no local information of the object, because usually objects are not squares. They're sort of round like the moon, or like here, the plane. These corners, they have no local information about where the plane is. And corner pooling is a method to propagate that information along the axis. So in corner pooling, what you would allow the location here in the CNN to do is to not only look at itself, so its own location, but actually to extend its field of view over to the right and down to the bottom. It's asked to predict a top left corner. So what you do is you max pool everything from here to this corner detector. So the corner detector will basically be able to detect whenever in either this band right here. So whenever in this band right here, there is the top, like the top of an object, like the top of the moon here, this corner detector can say, that's probably the right height right here for a corner. And it combines this with the information of this side here, where it also says, there is the side of the moon. That's probably the correct, up, down. So there's probably a corner right here, okay? Whereas a location right here would get the same signal from the right, or like almost the same signal plus this signal right here. But in essence, it would also detect the top of the moon, but it would not get the same signal from down here. And therefore it says, even though to the right I see the top of an object, I don't see the left of an object to my bottom, so I'm not going to predict a corner right here. Right, so this corner pooling goes for the top left, and of course equivalently goes for the bottom right. That can always max pools to up and to the left of itself. And that's exactly what you see here. So in this corner pooling, what you can do is you can propagate signal to the left and to up, and then you add the two informations, and that will give you your output feature. And you can calculate this actually fairly efficiently by doing like you do a cumulative sum, you do like a cumulative maximum across the different axes, and then you simply add two arrays, and that's it. So you simply put the corner pooling before you predict these different outputs right here, the heat maps and the embeddings, which means that this hourglass network is not affected by this. Just the predictors of heat maps and embeddings, they then get the information from this hourglass network into these directions. Okay, I think that's a pretty neat method of solving this, and here they show how you can calculate this, and then the corner pooling is right here. They do add a skip connection here because sometimes if you just aggregate this information, you might actually get confused, because so the trouble of course comes when there are multiple like different objects that have the same top, and then there's also a person right here that, so it gets like a signal, it gets another signal that there is the left side of a person right here, or maybe not like this. So it will predict like a corner maybe here where there is none. So it's sometimes it is important to have local information still, And that's exactly what this skip connection is supposed to address. I guess the situation up here would be resolved by the different embeddings, but still. So you have that, you add and you put another bunch of convolutional layers on top of that, and then you'll get your predictions. And that's it. You mix all the losses. So there is a detection loss from the embeddings. There's the, from the heat maps. There is the pull and the push losses for the embeddings. And there's this offset loss that you train to compensate for the downsampling errors. And that's it. And they ablate the various things here. Basically, they show that they're better than other one-shot or one-stage predictors. So apparently there's one-stage predictors where you have a single pass through a neural network, and there's two-stage predictors where you have multiple or two passes through different neural networks, and they compete in the one-stage neural network category, if so to say. And they show that they get significant improvements with and due to this corner pooling, which is pretty cool to see because it makes sense. It sort of makes sense how you would like to think about it like this, and to see that it helps is pretty neat. Yeah, they also investigate how large they have to make these Gaussians and so on. And here are some qualitative examples. You can see that without the corner pooling, what you'll get is, so the top here and the left and the right are detected correctly, but you can see that probably the network thinks that there is an extension of the object right here, and therefore doesn't do good job, because this position right here, it has no access to sort of, it has to use like a long range access. It can't really look in detail at the features here or here. So when it scans up and down this side where the bottom break is, it can only look at very coarse features, because it has to basically transmit information in the CNN of a higher layer, and the higher layer has a higher receptive field, which means it has a lower resolution. So it can't really go and look in very detailed fashion at this border right here. So it misses it. Okay. The same right here, as you can see. So there are a number of failure cases that they can now solve using this method compared to if they didn't use the corner pooling. They show some times where their method fails. For example, here it matches the top left and bottom right corners of two different objects because their embeddings were close enough. And yeah, that's what I'm saying. I'm wondering what these embeddings actually learn, because they are generated independently, so not entirely sure. It's also not exactly what I had in mind when I formulated this idea in the last video, but I'm actually not sure what I had in mind myself, to be honest. But in my mind, it seemed to be like you should be able to train a network if there is an object right here. You could train a network to predict for any given location, let's say how many pixels to its bottom right, or maybe you want to normalize by the area that's there, are part of a particular object. And then you could predict each pixel and use like the differences between the points as scores for bounding boxes. I don't know if you see what I mean. You could basically tell you'd have one network predict everything to the bottom right, and then you'd use the differences. And the transformers would be very good at that, because they can sort of have this attention between each pairs of points and so on. I'm not entirely sure, but this might just be crap. Yeah, here's some more examples. This appears to work really nicely, but of course in the qualitative qualitative examples, it always works nicely, but they also demonstrate it. All right, I found this paper all in all pretty cool, pretty neat. It's a simple idea. It's executed well. I don't have the feeling that there are like too many tricks in here, and they show really that the improvement seems to be due to their corner pooling method, and that's pretty neat. So if you like this paper, make sure to check it out, and I'll see you next time. Bye-bye.